Welcome everyone on YouTube. So this is our 56th live stream geometry. We have 6 people, including me on, and I'm sure a few more will join later. So today, I got a number of different suggestions from participants on my channel, which I always like because it makes it easier for me when picking the problems. So 2 of them today I'm choosing from a certain user on the Art of Problem Solving forum that I don't know of, but those problems were recommended to me. And then another problem I'm taking from the Discord Geometry Olympiad. And the remaining problems I'm taking from the Saudi Arabia IMO selection test. So if you ever want to join this session, feel free to email me at mgreenb801@gmail.com. The sessions, they're on Sundays at 8 a.m. US Central Time. So I'm going to start sharing my screen. Hold on just a sec. So here's the first problem I chose. It looks maybe a little easier than the rest, although I haven't tried it yet. So we have a triangle ABC, and D is any point on the bisector of BAC. All right, so here's triangle BAC. Here's the angle bisector. So D can be any point on it. So we could let D be this point up here, for example, if we wanted. And then we reflect A over BD and CD. All right. I'm going to draw those 2 in. And I will reflect A. So that creates a couple isosceles triangles, A prime B, and let me make this look a little better. I think that looks kind of good. So this is E, and this is F. And AQ is the external bisector BAC. So basically AQ is perpendicular to AG. All right. Hey Con, thanks for joining. So we're on the first problem. Okay, so Q is on BC. Okay, so we want to extend BC, and then we want to show EF and Q are concurrent. So B, G, Q, and C are in harmonic conjugation. Let me hide a couple things. All right. So there's a right angle right here, and ABE and ACF are isosceles. This actually looks a little bit familiar, I feel like. So yeah, I don't think ED and F aren't collinear. QF and E are. That's what we have to prove. Can we use cross ratios somehow? So I wonder if we let FE intersect AG at a point. like for example, if we do something like this, let's see, maybe we could show the cross ratio AQ, AF, AH, and AE is yeah, actually, I'm not sure.
AQ is tangent to the circle through AE and F.
Okay. So that might help. So yeah, then maybe it's like power of a point somehow. How did you is that kind of just an angle chase? Looks like it.
It is pretty obvious because D is the circumcenter of that circle.
Yeah, because D
because
is
of the reflection.
Yeah, because DA equals DE equals DF. So yeah, so it has to, since it's perpendicular, it's tangent. It's true. It's a good observation. So maybe the radical axis theorem somehow. Is there any circle that goes through E and F? Oh, I wonder if, no, I don't think that's cyclic. Wait, do those intersect on the circle? No, because if you do it like, but wait, I don't think this intersects on the circle, right? Oh, maybe it does. You think that intersects on the circle? See, it doesn't, because if you zoom in a little bit more, yeah, it doesn't. Hey, Melek, thanks for joining. So, okay, so QA is tangent to the circle. Is AG a symmedian? Doesn't look like it. I wonder if we could let EF meet BC at Q prime, and then we want to show that Q prime A is tangent. Wait, actually, so what if we label this point right here? I hint that it's called I. Let me just rename it as J. So basically, so the cross ratio QFHE, like AQ, AF, AH, AE. It's, if you project onto the circle, it's A, F, E, J. And then I don't know if we can use it as an angle bisector. I don't think, yeah, no, these triangles aren't similar, obviously. But basically, like if we let EF meet this at Q prime, we want to show that the cross ratio Q prime BGC is the same as the cross ratio Q BGC. Maybe that's one way to do it. Because what I kind of like about that so the cross ratio QBGC is the same as AIJK. Well, it's one. They're in harmonic conjugation. But if we let so I mean basically, I think a better way to do it is we let EF meet BC at Q prime, and then we want to show Q prime BGC is in harmonic conjugation. And is there somewhere we can project onto? That's not easy to see. I wonder if CV.
Can you check for me that if the line IK pass through the midpoint of Q prime G?
Yeah. So, whoops.
Michael, I think I've solved it.
Okay.
Wait, let me check for a second first.
Oh, no, it's not. Hold on one sec. So I wonder if C, D, and L are collinear. But after that, I'll get to this. Oh yeah, they're not. So what? So what's your solution?
I'll draw the perpendicular through A to EF, and it intersects the circle of AEF at a point.
Okay. Hold on just a second.
Through A and perpendicular to DQ.
Oh, DQ. Interesting.
Yeah.
Okay, so I'm going to get rid of Q prime and just call it Q.
Yeah.
Hold on a second. Okay. So we draw the perpendicular to DQ.
And it intersects the circle of AEF at a point.
So yeah, I wonder if, I'm just curious, is QJ tangent to the circle?
Yeah, obviously.
Yeah, by symmetry. Oh no.
No, the point that the perpendicular line intersect the circle
is tangent. Yeah. Okay, so QL is tangent to it. So QAL is isosceles.
If we can show that AELF is a harmonic quadrilateral, then it will be done, right? So I will prove
AELF.
Yeah, AELF. So it is the same at proving that AQ, AL, AF, and AE is a harmonic bundle.
Okay.
So this is true because we have AL is perpendicular to DQ, AE is perpendicular to DB, AF is perpendicular to DC, and AQ is perpendicular to DG. And however, DQ, DG, DB, DC is a harmonic bundle. So yeah, we have the.
Wait, did you say DQ, DB, DG, DC is harmonic?
Yeah, yeah.
Ah, okay.
So the line through A perpendicular to those four rays must be also in harmonic bundle.
Okay, so basically, so we know AQ, AF, AL, AE is harmonic, right?
Yeah.
And then if that's true, then that proves.
Project onto the circle.
Okay. So if you project through the circle, so I'm trying to see. So I understand. So let's see. Basically, we proved AELF is harmonic because if you look, AF is perpendicular to DC, AE is perpendicular to DB. AL is perpendicular to DQ, and AA is perpendicular to AG or to DG. So yeah, so okay, so then we know AELF is harmonic, and so how does that show that?
Well, so because AFLE is harmonic, so the tangent from A and L must intersect on EF. However, Q is the intersection of those two tangents, since QA and QL are both tangent to the circle.
Ah, now it makes sense. That's a really nice proof. I like it.
Yeah.
That's very creative. All right, so I'm going to move things around a little bit just to make room. Let's see. That looks better. There we go. Okay, so let the perpendicular from A to EF to EF meet
at to DQ, I think.
EF.
You tapped it wrong.
Oh, I'm sorry, A to DQ. I keep thinking it's EF. Okay. So yeah, good point. So A to EF. Meet the circle AEF at L. And that looks better. I don't want L to look like it's on this. Then, okay, so we know that BCGQ are in harmonic conjugation. That's well known. So I'm actually going to write that up here. Well known since, I'll say since AG and AQ are internal and external bisectors. Okay, and so then we have AF is perpendicular to CD. AE is perpendicular to BD. And then AL is perpendicular to DQ. And then AA, which is the tangent at A, it is perpendicular to AG. Okay, so thanks for joining, Sardar. It's been a while since I've seen this technique used. So basically, since they're all perpendicular to, or DG, I should say. Sorry, I see the chat. AF, CDBD, yeah. So since they're all like mutually perpendicular to the 4 lines through D, the angles between these are the same. So that means that AF, AE, AL, AA. Yeah, it's an interesting idea. So we have basically, I'll write it like this. So BCQG is equal to BCQG, which is equal to A. So that would be EFLA. So I could write it like this. So that means that AFLE is harmonic. Harmonic quadrilateral. Yeah, this is a really clever trick. And so once we know that, basically by symmetry, since QA is tangent to the circle, okay, so yeah, first why don't I write that like D is the circumcenter of that and QA is tangent. So I kind of skipped a step, but I'm going to write it now. So DF equals DA equals DE. So that means D is the circumcenter of the circle AFE, and so QA is tangent. So implies QA is tangent to ADE. So basically, by symmetry, QL is also tangent to the circle. And then once we know that, that means that EF passes through Q. Okay, so I could say EF and the tangents at A and L concur at Q, which is the same as saying E, F, and Q are collinear. All right. Very nice. So I will move on to the next one. So the next problem I think is a little bit harder. Let's see. Yeah, so I don't usually do AOPS, but this was posted on Discord and it looked like a nice problem. So yeah, all right. So here's the next problem. Okay, so this is a tricky one. So Stefan said he solved the first half, but not the second. So we'll see how far we can get with this. So we have a triangle ABC with in-center I and circumcircle omega and circumcenter O. All right. So I'm going to draw the in-circle. And I is the in-center. And then we could draw the circumcircle. And O is the center of that. So O is the center of circle B. And it touches, the in circle touches CA and AB at E and F. So that's E, that's F. I wonder if I should just draw a point D just to draw it. Whoops. So R is another intersection point of the external bisector of BAC with the circle. Okay, so basically it's the midpoint of arc BAC. So let me close this. All right, so I'm going to draw this point. Actually, let me just do it like this. So this should be R. So basically angle RAG is 90 degrees. And then we draw the mixed linear point. Okay, so we know by theorems on mixed linear in circles that this is going to be T. It's where RI intersects the circle. W, I don't know if I want to draw. I'll draw the mixed linear in circle. So that would be basically the circumcircle of THJ. Whoops, didn't mean to do that. Okay, so we have the circumcircle of THJ as the mixed linear in circle. Let W, X, and Z be points on the circle. Okay. So it says E, F, X, and Y are cyclic. So we want, oh, but Y isn't necessarily in a circle, but okay, but W, Z, E, and F are cyclic. So that gives us some information. So let's see. So how do we do this? So we could call this W and that Z. And it says EF, so RX intersects AI at Y. So there's some other point X and it intersects AI. So Y is somewhere on this, and EFXY is cyclic. Okay, so basically X is the intersection of EFY with the circle. But it says AZ, EF, and RX are concurrent. Okay, so that kind of, so this is AZ, and then EF, we draw like this. So basically X, wow, this is complicated. X would be the intersection of RK with the circle. So this would be point X. And then, yeah, this is worded really weird. And then we have EFXY is cyclic. So
Y is easy to draw. It's the intersection of Rx and AI. You can first draw Y.
Oh yeah, you're right. I can first draw Y. So that is going to be point Y right there. And then they want EF. Oh, okay. So this is why it's tricky, because it's like you have to kind of play around with the diagram to make it cyclic. So I'll try that. So we need EF, X, and Y to be cyclic. What if we... Let's see.
Draw the line KR and not the segment. That is why the circle is disappearing.
Okay. So I'll draw the line KR, and it intersects the circle at X, and it intersects AI at Y. And we want EF, X, and Y to be cyclic. So I'm going to try to move, if I move W around, it's almost like, yeah, I don't know if I want to make the triangle like, make it like taller, maybe.
Yeah, taller is better, I guess.
Maybe like this. So we have EF. It almost looks true there. But if I make it taller, the points get really close to that.
Taller is not better, okay.
I think the problem's more like closer to being true when it's taller, but let's see.
I think you should move the W point like down there.
Let's see. So if I move the W point down, then but then EFXY. This is hard. Let's see.
Well, Z is not variable, so we can draw a circle of ZEF.
ZEF.
Yeah. Okay, we draw it.
Oh yeah, I drew it. So we want EFXY to be cyclic. Let me go back to.
Triangle is too close to being isosceles.
What if I do an obtuse triangle like this? So EFXY. No, that doesn't look cyclic. Oh, actually, yeah, that's.
Also, Michael, keep in mind that R is different from X.
Yeah. So
now can you move W? Only W.
Yeah.
Yeah, they are too close to A, but
They're too close to A, yeah.
it has to be, I guess.
Yeah, that might be the only way to do it. Let's see. Yeah, it's kind of something like that. So yeah, maybe I'll just leave it like this for now. Let me hide stuff to make it look nicer. So I don't need that. I don't think I need that. Okay, so I want to draw X, Y, and R. Well, oh, I need to show the concurrence. So I want AZ, I want AZ, EF. Oh, that's why I drew those three. That makes it annoying. Because I want those to concur. But then I also want EXFY to be cyclic. Okay. See if it's cyclic, then they're very close to A, and then it's hard to see where it concurs. So it's a hard diagram to draw. Maybe we'll just have to know that they concur, those three lines, like without seeing where that point is. Or maybe, yeah, we'll just have to keep in mind that they concur. So the first thing is it says prove that AZ, RW, and OI are concurrent. That doesn't even look true. Let's see. So yeah, maybe I didn't really draw it right. So let's see, EFXY is cyclic, and WZEF is cyclic. RX and AI intersect at Y. We want to show AZ. Yeah, that doesn't look true that AZ, RW, and OI are concurrent. So maybe I didn't. Should we draw Y and don't care about concurrence? Maybe we could. Wait, but XY, wait, AZ, RW, wait, AZ, EF, and RX are concurrent. And these don't even, I guess these lines are just really, really close. Yeah, maybe we should just draw point Y. I kind of like that. Or also, what if I move W over to the bottom? Kind of like, I don't know if Khan was the one who said that, but yeah, but then EFXY isn't really cyclic. Yeah, I don't think I should move W to the bottom. If I make it more obtuse, and then if I move, it's kind of like that, make it more obtuse, and then move W downwards. So now does it look true? So AZ, RW, and OI. But that, yeah, it's weird. The problem doesn't look true. I mean, I'm pretty sure it is, but yeah, maybe the only way for this to be cyclic is if Y goes like past A. So like something like this. So let's see.
And move W to the below, maybe. It can be useful.
Move W where?
Below. To the bottom.
Oh, okay. Yeah. Yeah, maybe W needs to be like somewhere like.
And continue moving around the circle, maybe there will be a better place.
Yeah, so let's see, WZ. What if I do so I want WZ, I want this circle to pass through Y. So I think maybe like this.
I think we should move on to the next problem.
Yeah, that's kind of hard. So AZ. So this diagram actually looks like it might be correct. I'm just going to check before I move on to the next problem. So we have AZ. Sorry, I already drew that. RW and OI. So this looks like it's probably the closest to being correct. So yeah, let's move W until those three concur. Yeah, so this is probably like the closest. Yeah, I think this is the best diagram.
You
Hold on.
have the linear circle. Like, I don't think that is gonna help.
Let's see. So AZ, EF, and RX. So AZ, EF, and RX concur at K. I'm sorry, what did you say? You don't think what's going to help?
Can we remove the mixed linear circle? Because we will use the T point.
I agree. We can remove the mixed linear in the circle.
Like, yeah, the first, like, we don't even use the point T to construct those points.
Yeah. So, oh yeah, like T isn't really used for T. We don't use for part A, so we can kind of hide that, and then hide that. Whoops. Sorry. I might move on to the next problem, but first let's see. I feel like this diagram looks a little better. So, okay, so we have RX, AZ, and EF concur at K. And it almost looks like these also concur. So maybe that's like something we have to prove.
Maybe the radical axis theorem will help. Like we use on the 3D circle, E passing through EF XY, passing to like WZEF and the omega.
And the whole circle? So let's see. So the three radical axes are, if we use the radical axis theorem, so let's see. The three circles are the big one, this one, and this one, right? So EF is one of the radical axes, right? And then, oh, but I think we'd have to draw this point, right? So this would be another radical axis. And then what's the third one? I think it's ZW. Yeah. So those would concur. So we could draw that point. Yeah, I feel like this diagram is about the best we're going to get. All right, I'm gonna let's do this for like 5 minutes and then I'll move on to the next problem. Because yeah, it could be that it's just like super hard, but this diagram maybe looks a little better. Maybe we can find a fixed point for W. So, okay, so at first I thought these three concurred, EF, RW, and AI, but now it looks like that's not true. At least I don't think so. Yeah. So we want to show that AZ. Wait, now it doesn't look like the problem's actually true. Wait, we want AZ, RW, and OI to concur. Oh, we must have, yeah, I need W to be like right there then. Okay, so whoops. Sorry, I see there's a lot of comments in the chat. Oh, I always use GeoGebra. I know it's kind of cheating because you don't use it on contests, but yeah, I finished contests a long time ago and I just really like GeoGebra, so yeah. Took 2 days to solve part 1. Then maybe we can move on then. Okay, yeah, let's come back to it later. All right. So here's the next problem. Yeah. So this was another one by the Caesar. So we have a triangle ABC with in-center I and circumcenter O. Let me first draw the circumcircle, and then I will use this tool to draw the incenters. Oops, it's not popping up well. There we go.
Actually, this is from a Taiwan mock, and we have done this before.
Oh, this exact problem?
Exactly. Is the exact one, and the solution uses A.
Uses part A. Okay, I'll move on to the next one then if we've already done it. So this problem looked kind of interesting. So I didn't realize Saudi Arabia has some really good problems. So Khan sent me like problems from Saudi Arabia, but they don't have just an IMO team selection test. They also have like team selection tests for a whole bunch of other competitions. And a lot of the problems look really nice. And they also have some problems that they just use for their training for IMO. So oh, whoops, it has to be a what do you call it? Not a cyclic quadrilateral, but it's circumscribed about a circle. So
tangential triangle.
Oh, this is China TST 12. All right.
No, this is not the previous one. Previous one is China TST.
So do you know if we already did this on the channel?
We didn't do it, I guess. I'm not
Okay.
sure.
Have you done it before?
No, I didn't.
Okay. All right, let's try it. Saudi Arabia, they need to make their own problems. I feel like they take a lot of problems from other countries. All right, so A, B, C, D. Oh, whoops, what am I doing? I want to draw the tangent at B, or I want to draw a tangent. Tangents. Something like this. Then I'll have to rename them. So A, whoops. It's weird. I think I have to hide. Yeah, the line, I don't know why I drew the line twice. So A, B, C, D, and then it touches the sides at M, N, P, Q. Let's see, I think I might have to hide something here too. Yeah, this is weird. I don't know why it drew the lines twice.
That is because of the tangents. It draws two tangents.
Oh yeah, you're right. Yeah, that's why I did it. Okay. So this is M, N, P, and Q. Yeah, I feel like there's not a lot of problems I've done on my channel that are circumscribed. I wish there were more because, like, yeah, I feel like it's a whole area that is kind of missing. So K and L are the circumcenters of AMN and APQ. So maybe I could draw this like, what if I did it instead like this? So something like this. So AMN and APQ, we draw the centers, K and L. And the center of this one will be L. And KL cuts BD at R. And AI cuts MQ at J. I'm going to show RA equals RJ. So this is J. That point way over there is R. Let's see if I can make it a little better. Yeah, if I make it more like this, maybe it's not so bad if R is like over here. Okay, let me make this diagram look better. I want to show RA equals RJ. You check that that's correct before I. Yes, okay. So, okay, here's AI. Hide a lot of different things. Whoops. Oh, I need to right click it, I think, to hide it. All right. This is an interesting configuration, very unique. So AMQ is isosceles, AI is the bisector. Let's see what we have in the chat. Yeah, I feel like there's a lot of really nice circumscribed like they should do more of them in contests. We used a point circle for a similar problem. So let's see. So J has the same. Is RA equal to RC? Let's check. I don't think so. It looks really close, but. Oh yeah, because R lies on KL, so that would only be true if C is on the intersection of the circles. That's a good point, Con.
It is probably good to label the other intersection point of those two circles.
Okay. So
because RA and R that point.
Yeah. No, that's a good point. So R would basically be the circumcenter of AJ in that point. Let me see if I can make C a little bit further away.
Can you check if R is like the center of homogeneity among the two circles?
Oh, that's a good point. I'm gonna check that in just a second. So I'm gonna, this is kind of close to C, but I'm just gonna label the point anyways. And then let's. I don't know why. There we go. No, R is not the center of homotopy. Let's check the chat. So let me see. Let me see if I can make C farther away from the circle. It's kind of hard to do that. Yeah, I think C is always going to be kind of close to the intersection of those circles. Yeah, it's not going to draw them unless I zoom in a lot. Sorry. Oops. So yeah, R. Basically, we want to show R as a circumcenter of AJE.
I think that circle. Yeah, I think that circle through that point with center is orthogonal to the in circle of that quadrilateral.
Okay. Interesting. Okay, so if we draw the circle through A, J, and E, it looks kind of orthogonal to the in circle. So that's interesting.
Yeah, that is true because you can just use power of point to prove it.
Okay, so that's just power of a point to prove that they're orthogonal.
Yeah, since like ij times ia is the power of point I, which respect to that circle, and it is also equal to the radius of I squared.
Okay.
Yeah, but still, we don't know that that circle passes through through A and J.
So yeah, because ij times ia is equal to I, like if we label this point, it would be that squared. All right, I'm going to hide the circle for just a sec. So I wonder if we let AD meet BC and AB meet CD, and we connect those two, I wonder if R relies on that. So maybe it's also worth letting, like, oh, actually, never mind. So J lies on the polar of A.
Label the intersection, unhide the circle.
Okay.
Now, if we label the intersection points that circle with the in circle.
All right.
Then P, Q, NM, and F, G would concur.
F, G, D, Q, and MN.
P, Q, and MN.
P, Q, and MN. Interesting. I think I'll just keep that in mind just because it would make the diagram hard, but that's an interesting observation. So, well, because GF is perpendicular to KL, right? Did you get that by the radical axis? Yeah, that's the radical axis theorem, right?
I did that by poles and polars.
Interesting. But I wonder if it's because you have the end circle, then you have this circle, it's PQ. Okay, so yeah, use poles and polars to do it.
I should also say that fact depends on the orthogonality.
Okay, and Khan proved that, so I think so we're good there.
But it isn't exactly like that because we like a bit used the fact we need to prove in the problem to prove that orthogonal.
Oh yeah, we use that it's the circle that it's cyclic, so we kind of cheated there.
So it is more like if we take the circumcircle of AGE and AJE and not consider that center.
Okay, so we take the circumcircle of AJE and then we let it intersect at F and G. And yeah, we have to prove R is the center, but then we know that PQ, GF, and MN are concurrent. That makes sense. See, so RJ. Okay, so we want to show KL passes through the circumcenter of AJE.
I think that AE also concurs with those three lines.
Oh, really?
It looks like it.
So maybe maybe it's worth hiding R for now and drawing that part of the diagram. Because if all those different lines concur, you said AE. I don't think AE and C are collinear, right? Or I would doubt it. It almost looks like A, E, and C are collinear.
I think that they should be actually. I think there is some theorem that AC concurs with that line, those lines.
Really?
Maybe by poles and polars.
Interesting. Yeah, it sure looks like A, C, and E are collinear. I'm going to hide R for now, just because so yeah, it looks like A, C, and E have to be collinear. Okay. So, and then we have P, Q, M, N, and was there another line too that you said FG, right? So these would all concur. I want to make them concur, but let's see. How do I? Let me do it like this. So if I do like a really, maybe something like this, and then I could shrink it. Sorry, this is so messy, I know. This doesn't look so bad though. I kind of like this diagram right here. Let me
that AE is concurrent. That is actually just radical access theorem.
okay.
But I think I'm not 100% sure that the proof I came up with for that GF also concurs doesn't use the fact that we should prove.
Okay.
So maybe that is something it is sufficient to prove. I'm not so sure.
That could be sufficient. Yeah, you're not sure yet. Okay.
And also, I'm confident enough that I can prove that AC concurs. So A, E, and C should we can prove that those are collinear.
Okay. All right. Let's see the chat. The Apollonius circle and circumcircle are orthogonal. That's see who's on. Yeah, this looks kind of familiar, this problem. Like not the exact problem, but like showing that RA equals RJ like this. Hmm. Yeah, this looks hard. Let's see. Okay, so we draw the we want to show the circle of AJE is orthogonal to the end circle. So yeah, if we could just forget about R for the time being, if we I wonder if there's just a way to show that the circumcircle of AJE is orthogonal to the end circle.
We have proved that.
We've already proved that.
Yeah,
Okay.
that is like true for every circle that passes through A and J.
Okay, every circle passing through A and J is orthogonal?
Yeah, because you
Interesting.
can calculate the power of point I, which respect to that circle, and it will always be the radius of circle I as well.
Oh yeah. Yeah, no, that's a good point. Yeah. One sec, guys, I'll be right back. All right, thanks for waiting. So yeah, I wonder if we let AD and BC intersect and AB and CD intersect. I wonder if that line passes through R. I don't think so. No. But maybe it passes through some other point. So we know RG is tangent to the end circle. We want to show
Do we know it is tangent?
yeah, we don't. Yeah. Only if we define R to be the center of that circle. Yeah, but that's not how we defined it.
Maybe some insight about what I was thinking while adding that GF line will help. So we will take polars with respect to in circle.
Okay.
So I think you don't need to draw anything.
Okay.
So NM is the polar of B.
Mm-hmm.
So so B lies with the polar of H.
Mm-hmm.
And similarly, D lies in the polar of H because PQ is the polar of D. So BD is the polar of H. And we know that R lies on the polar of H, so H lies on the polar of R. And then comes the orthogonality. So like RG and RF should be the tangents, and if they are, then they should concur.
That makes sense. So we know that H lies on the polar of R, or with respect to the in circle. So if we know, basically, if we know H, F, and G are collinear, yeah, I kind of see what you're saying. I think that's a good idea. So yeah, we want to show that FG is the polar of R.
Michael, can you draw the diameter of circle R? Diameter passing through A.
Okay.
Then MQ must passes through that point.
Oh, really?
Yeah, but just because the right angle, I don't know if it can help, but maybe we can, figure out more about a circle.
Yeah, it sounds like a good idea. So I'll call it P for, well, T maybe. Yeah, because this is a right angle. So RA equals RJ equals RT. Yeah, that makes sense. I wonder if TI and RK. It's probably a coincidence, but I'm just curious. Yeah, it's a coincidence. I like Stefan's idea. So we know that R lies on the polar of H.
What if we let R dash to be the intersection of A external angle bisector in BAD, and then the circle will be orthogonal, and if we try to show that C has equal power with respect to all the circles.
Okay, so wait, so you said draw the external bisector of BAD?
And then try to show that C has equal power with respect to the three circles. Then KL R dash will be collinear.
Okay. So okay. So this is the external bisector, right? And you said, did you say you want to see where it intersects the circle ABD?
I mean external angle bisector of DAB.
DAD?
DAB, yes.
DAB. So that's this line right here that I just drew. And then where do you want to see where it intersects? Like, do you want to see where it intersects this big circle, or?
Oh, sorry, maybe wrong.
Oh, that's all right. Well, what were you thinking? Like, you wanted to see where it intersected this circle right here? That's all right. It looks like that point might be collinear with J, R and J. Let me check it out. Oh, yeah, that's kind of odd. Well, because yeah, if R was the center of the circle, that would be true, because this would have to be a right angle. So yeah, it could help.
Is RA tangent to the circle ABD?
I don't think so. Or let's see. So if I draw, it intersects it again.
Oh yeah.
Okay. So someone in the
If you
chat.
figure out a way to use R, like it's the intersection of LK and BD. I still haven't figured that yet.
LK and BD.
Yeah, we haven't even used like how point. We didn't even know how point R works.
Yeah. So Stefan suggests, why don't we move on to the next problem, and then we can come back to this one later. Oh, we're already on the fourth one. So wait, we solved, oh, because that one was on a previous one. Did it delete? Okay, never mind. I still have some problems here. Okay, so let's see if we can do this one. I think this might be a little bit easier. We have an acute triangle inscribed in a circle O.